good afternoon to everyone. My name is Lakshmi and I am a student of the EEE department. And this was a part of my 8th semester final project that I did here. And this is Devdutt. We both did this project under NIYANTRA. And what I wanted to concentrate on was a virtual power analyzer. Now, where does a power analyzer come in? It's basically an instrument that is used to monitor power quality parameters like your voltage, your current, and the quality of power that's coming in from the supply or across any terminal that you connect it across. It gives you the value of the, like I said, the voltage, the power, and it also helps you determine if there is any particular sag or swell. These are just events that occur in any power quality system. A voltage sag is basically when the voltage drips below a particular threshold, and a voltage swell is when the voltage goes above a particular threshold. So we have all of these parameters affecting our everyday power quality system. Like the one we get at our supply here, this 230 volts AC volts, it's affected by a lot of parameters. It can be even lightning for that matter. That becomes a voltage surge in lightning, which if it gets hit by lightning. So this is basically a tool to monitor these parameters, and in the next half an hour or so, I'll just take you through the basic functions that the VI implements. Okay, so now what is this virtual power analyzer and why is it needed? We already have something like the fluke meter and something called the Yokogawa three-phase meter. I don't know how many of you have heard of it, but these are existing meters that already do this job for you. They are basically the power quality diagnostic tools that we use these days. But why would we go in for something like this when you already have those in front of you? There are a few reasons for that. The conventional power equipments have fixed vendor-defined functionality. Let's just take a simple multimeter. It will not measure a current which is more than its range. It is defined for a particular range, and that's the current it will measure. It will not go beyond that. So the functionality and the specifications cannot be modified in them. They are hard-coded. Also, you cannot store the data for future reference. And even if you do, it's for a very small data memory. You need to put in like a really high, memory card onto that, something of a high value, for you to be able to do that. And that's not really available with the fluke meter and the Yokogawa meter, for example. So that's where this comes into picture. That is the LabVIEW software and the virtual instrumentation. What it does is reduce development time. You're using it on a software, you're simulating it and you're testing it on the real-time systems. And also the associations are not fixed and it's managed by the software. So you can modify your program according to your own wish. You can vary the ranges that you need to measure. This same system can be used for a three-phase system as well. What we've developed here is for a single-phase system, and you can go ahead and work on a three-phase system as well. So the associations are you can modify them to your own needs. You can just put in whatever you require on different systems. And also the third thing would be the digital over analog concept, wherein we all know that the digital ones are more flexible and they are more easier to use than the analog instruments. So this gives us that flexibility and usability. So what we've basically done here is use this LabVIEW software and created an interface for simplified design implementation and measurement of these parameters like the power and voltage current, etc. So what we've done further is 3 steps that go beyond it that we've been seeing in the last 4 days. There's acquire, analyze, and present. So how do we go about it? The signals are acquired using sensors, basically from the system. For example, I have that supply there. I have sensors connected to it so that I can sense the voltage and current that's coming in from the point of coupling. And that is then interfaced, that's connected to a DAC. That's the data acquisition card that we use. And that interfaces the computer and the sensor so that we can take in the readings into the computer and then analyze it. I'll tell you how that goes. So, like I said, the sensors for measurements, and then comes the data acquisition part. And then on the computer we have the power analyzer, which is used for the display of all the parameters. I'll show you screenshots of everything so that's more clear to you. So, just to tell you, this is the point of coupling, then it goes on to the sensors. And from the sensors, the signals are taken by the acquisition card and then onto the LabVIEW software. This is just a picture of the voltage sensor that we've used. This is basically the LEM 25600 transducer. Measures up to 600 volts nominal. And this was a sensor which we use for voltage measurements. Similarly, this was the current sensors that we've used here. And then coming on to the DAC card. The DAC card that we've used here is the National Instruments 9239 data acquisition card. It has 4 channels, USB carrier with a 24-bit resolution, and one very important thing about this card is the channel isolation facility. This can provide for channel isolation, which is very imperative for our project that we've done. I'll tell you how it is, because when we first started out with our project, we used the 6008 card, the NI 6008, the card, the small white one. I think we are familiar with that now. That's the 6008 card is what we have used initially. For a single signal, like if you're just taking a voltage signal, it's really good. It's ideal. It's inexpensive. You can use it for just a single signal acquisition. But where does it not help you is for the measurement of simultaneous sampling. Since our project deals with power, that's voltage into current, we need the voltage and the current to be synced. They should be at the same frequency and at the same time. The amplitude and the frequency should be the same. And that was one small glitch which we found with the NI 6008, and that's why we went on to use the 9239 card, which helps us, and it has the channel isolation, and it also has the provision for simultaneous sampling. Now, and this NI 9239 DAC is mounted onto a particular chassis, that's the NI CDAC 9184 chassis. And it's mounted onto this DAC so that the interface can be completed and you can conveniently plug it into your computer. And also, this one is an Ethernet chassis. So that one very good usage of this is that it provides remote sensing. So what you need not really have to be there in front of your inspection place for you to measure it. For example, if I have like a power plant, for example, and I'm trying to measure the voltage or current there, I don't actually have to be inside the power plant at that exact supply place. And for just, let's take a simple example. Right now, this setup is in the PE lab on the ground floor. And I will be running this code here, and we'll be able to see from here as to what is the exact scenario there. So remote sensing is possible with this. This is a screenshot of the DAC I've been speaking about. This is the NI 9239. It's got 4 channels. And this is the CDAC 9184 chassis. It's got 4 slots in it on which you can place 4 of these cards. And as we've seen, since it's an Ethernet-based system, we need to make sure that the communication is established with the card and the target computer.
Good afternoon, everyone. I'm Devdutt. I'll be talking about hardware implementation. So how do we go about implementing it? As you can see in the diagram, this is a 230 volt single phase supply. This is a current sensor which is in series with the circuit. Here we have a LV25600 voltage transducer which is connected parallel across the load. Now, voltage across this resistance is fed to the channels of the DAC card. This is the screenshot of the setup. Software implementation. So what functions does the virtual power analyzer developed by us provides? We can measure different system parameters. Now by system parameters I mean voltage, current, power factor, power, active power, reactive power, harmonics, and power quality event detection and data logging. Now what do we mean by event detection? What are the types of events that occur generally? There are 3 types of events that occur: interruption, sag, swell. Now what is interruption? So generally we use voltages which are 230 volts single phase. Now how do we define an interruption? If the voltage falls below 0.1 pu, that is less than 23 volts, it is defined as interruption. If the voltage is between 0.1 to 0.9 per unit, that is 23 volts to 207 volt, we classify it as sag. If the voltage is between 207 and 253 volts, we classify it as normal working voltage. If the voltage exceeds 253 volts, we classify it as a swell. Now this is the basic flowchart of our power. Here we have acquired voltage and current, taken out the phase difference, found out cos and sine, multiplied voltage and current, found out active and reactive power. This is the flowchart of event detection. As we can see, if the voltage is less than 0.1 per unit, 0.1 pu, it is an interruption. If it is greater than 0.1, less than 0.9 pu, it is in sag. If it is greater than 0.1, less than 1.1 pu, it is normal. If it is more than 1.1, it is well. This is the block diagram of the virtual power analyzer developed. This is the block diagram of the event detector used by us. This is the block diagram of event logger. Results.
So, like I said, there are three parts to it. First is for the power, the voltage and current measurement. The second one is the event detection, that's sag and swell. And the third part is where you just see the event logging. You're just trying to log the data that you just sent so that you can use it for future reference. That's a data storage part of it, and that comes under the event logging part. So for our project, what we did was that we tested the setup that we had created, and we also compared the results that we got against the standard existing meters, like the Fluke meter. We used the Fluke 43B model, and also for the other measurement, we used another meter. It's called a Yokogawa 3-phase energy meter, and that was a CW214 which we used. And we compared the results of our virtual instrument against these, and they were found to tally. In the next 15 minutes or so, we'll just try to give you an example of one or two loads that we took as testing it against those two loads. For our project, although we did go about three different loads. One set was a linear load, that's 3 incandescent lamps, and a 65 watts pedestal fan. That's what we use as a linear load. A non-linear load was the laptop load, the SL400CL, just a general laptop, and another one was a CFL that we tested. So we used different combinations of these loads just to see how the system's behaving and how we're getting a right output or not. And we'll provide you a glimpse with one or two loads as an example now. So since remote sensing is available, we can just run, I can run the program here, and I'll be able to show you all the results on the screen now when I run the VR, because the loads etc. are being changed in the PE lab downstairs. And if anybody wants to go ahead and just see the setup of the hardware, you can definitely do that. After the session's over, please meet us in the PE lab that's on the ground floor. And after the valedictory function, anyone who's interested can just come up there, and we'll be able to explain to you the exact setup, the one which you've seen earlier. This is the system setup. This is the exact system setup which we have downstairs. So this here is the card, and these are the sensors, and there's the loads that we have here. So this was the incandescent lamp, the fan, and the laptop loads, all of which were used as loads to just compare and test our setup. Please give me just 2 minutes while I just set this up, the VI.